In this chapter, we're going to look at the ways in which atoms seem to be held together within molecules and take it to the next level. In chapter 8, where we learned about the valence shell, electron pair, repulsion model, we're going to take this to the next level. In my mind, this leads right into what we call orbital hybridization. There's going to be an awful lot of overlap. And if you knew anything about both of these ideas, that was a pun. Then we're going to look at another idea. This is the first part of the chapter, the majority of the chapter. The second part of the chapter, we'll be looking at something called molecular orbitals. And we won't spend a lot of time on molecular orbitals. Up until a few years ago, molecular orbital theory wasn't on the AP exam. In the last couple of years, I've noticed some small questions having to do with molecular orbital theory on the AP exam. Now in this picture, you have a picture of a complicated molecule that is actually a Nobel gas forming a compound at just the right temperature and just the right pressure. This was first discovered back in 1962. So the idea that inert gases can actually make compounds has been around for a while. We always think of inert means it does not react, and for the most part that is accurate. Certainly the first two elements in the noble gas column, helium and neon, don't form any compounds that I know of. Then when you start to get to the next element in the noble gas column or family, argon, we start to see more and more possible compounds, if the conditions are right, that can actually be formed with inert gases. But this first compound from 1962 is right here. And in a later chapter, if you were going to learn a lot about the nomenclature of transition metals, and platinum, by the way, is a transition metal, they talk about all the rules for naming these complex polyatomic ions. The name of this particular ion happens to be xenon, and then we use the word bis for 2, pentafluoroplatinate. And in here, you have 2 pentafluoride fluoroplatinate ions connected to your xenon. Now, you don't have to know that. This is something that would be more relevant in I think it's chapter 22. But you would learn how to name these by looking at the formula, which I just did, or how to write the formula from the name. And the tricky part in this is you'd have to break up. They put the 2 platinate fluoro ions together, and just instead of PT1 with a bunch of fluorines, they put the 2 together. So in any case, that's neither here nor there for our purposes. And to my knowledge on the AP test, they don't ask you to name complex compounds like this one. In any case, the point being, we now have compounds out of some of the inert gases. And of course, every time we discover a new compound, it is important because it might have some interesting properties that we can take advantage of. So again, just how are molecules held together? What is a bond? Remember, we're not talking about what connects one molecule to another as much as we were talking about a more advanced way of understanding how the atoms within a molecule are held together. Now, there are literally millions of organic compounds and hundreds of thousands discovered every year. Where do we discover new organic compounds, or any compounds for that matter? Well, sometimes they are synthesized in the lab. We don't know whether or not they exist in nature, but we can synthesize them in the lab, and then of course we have to identify them with our various devices like a mass spectrometer and atomic absorption, look at the atomic absorption spectrum, other types of devices. Or We go throughout the environment and we find in various plants and various animals various exotic proteins or compounds. And once we elucidate them, figure out what they are and what their structure are, then we can see if they have any valuable properties. We're going to find out that the orbital theory, which we're going to look at mostly, pretty much explains the vast majority of compounds that we might think about, but it does not explain some of the other properties or compounds that we find. So the valence bond theory, right here, is the first one we're going to be looking at. We'll be talking a lot about orbitals, and this is the second one, the molecular orbital theory. You already know that the first theory, again, Linus Pauling, we've talked about him in the previous chapter a little bit, and then the latter theory is by an American named Robert S. Mulliken. Mulliken, by the way, was a Christian, but he was what we would call a theistic evolutionist, and that's an interesting subject to study sometime if you're interested in these kinds of debates about just how does God act in nature. And we have all of these ideas coming out of the Darwinian evolutionary theory, and it all requires spectacularly impossible occurrences, statistically improbable connections, mutations that are beneficial, that can create ultimately, if you get enough of them, new body plans and new proteins and new structures. It's a theory that is pretty much dying, by the way, because there's just no evidence for it at all. And it's hard to think that all of these accidents and chance occurrences can produce anything of substance and any kind of information at all. But a theistic evolutionist, sometimes called an evolutionary creationist, would say all of these impossible things are happening continuously all the time as evolution in the broader sense goes forward, because God is making it happen in the background. And do not concur with this kind of idea. I think it creates or implies a rather deceptive God, and it makes science rather impossible, or an endeavor to try to figure out something that can't happen by ordinary processes. And we're always invoking God working, making impossible things happen on the molecular basis, moment by moment. And I don't think that's a reflection of the character of God. Plus, I think that, again, evolutionary creationism is just trying to create the perception that the broader evolutionary paradigm can happen, and you're just sort of baptizing it with some theology. But be that as it may, let's get a move on here. So one other thing about Robert S. Mulliken's molecular orbital theory, you're going to see this word delocalized a lot. We've already referred to electrons being delocalized in metals, where you might have, if these circles represent the nuclei of metals in some type of pattern or crystalline structure, and then the electrons are all over the place. They are delocalized. They are not held in place in specific orbitals with the nucleus of each metal atom at the center. And because these electrons are delocalized, they are able to move about a lot, which is how we can talk about the conductivity of metals, both in terms of conducting electricity as well as conducting heat. Also, why metals might be shiny, because you have electrons jumping around all over the place from energy level to energy level. Well, in this case, we're using the word delocalized to talk about orbitals being delocalized as opposed to electrons being delocalized. And hopefully more about that later. So why do we have two theories? And this is something that happens on a regular basis in science. One theory can explain a lot, but it's not sufficient. So we have another theory that can explain other things. Sometimes these two theories seem to be at odds with each other. If you think about the two primary theories about what is light, light is made out of particles called photons, or light is made out of waves. And so we have the definition that I use and invented for my students, and that is light is particles or packets of energy called photons, which have wave-like characteristics. And we learned about that back in our unit on quantum chemistry and quantum mechanics and quantum physics. So the valence bond theory is what we're going to look at the most. The molecular orbital theory we will look at briefly. The molecular orbital theory does explain things we can't observe, such as molecules that are in higher energy excited states. It can explain why liquid oxygen seems to be paramagnetic. It also helps to explain colors. So that's the idea why we have these two different models or theories, because one just isn't sufficient enough to explain the complexity of God's creation. Now over here we have a quote by a C.A. Colson. I don't know much about him, but he says this: a chemical bond is not a real thing. It does not exist. No one has ever seen one. No one ever can. It is a figment of our own imagination. And so much at this atomic and subatomic level has to do with our mental models of things and their relative explanatory power. And you can know things that exist without necessarily seeing them with your eyes. Maybe you're seeing them indirectly by using devices that look at the light that is beyond the visible spectrum. And a lot of times we use computers to take the electromagnetic radiation that we can't see and give it a color so we can get some mental pictures of it. So let's dig in now with the valence bond theory. Valence bond theory is about the overlapping of orbitals. And in class, depending on when you're reading this, I have already demonstrated, or I will demonstrate, what happens if you take two balloons and you push them together. So imagine I have one balloon here, and here's the little part that's tied off, and here's another balloon here, and here's the little part that's tied off, and then I push them together. And when I push them together, it looks something like this. Obviously, I can't make the two balloons merge together to become one balloon, but you end up getting what we can imagine is the shape of two orbitals that have come together to make to overlap each other and create the region of space where the electrons are likely to be found in this bond between two atoms. And of course, these two balloons are circular. And so we would think of these as being S subshells that are circular. But imagine I had a balloon, or imagine I took two balloons and held them together at the very center. There are two places where you tie them off at the center, and say this pair of balloons represents one P subshell, a barbell subshell. And then I take another pair of balloons and I say this is another P subshell. Not two P subshells, 1, 2, but a single P subshell, barbell shaped. And then I bring this one together, and then I bring this one together so that this region here and this region here are pushing against each other. Now I've created a overlap between two P orbitals, one around one atom, one around the other atom, and this creates a bond made out of two P orbitals. We could also do something like this. We could take a balloon representing an S subshell and another pair of balloons representing a P subshell, and we can bring them together. And this then, when we push these two orbitals together, my S orbital represented by one balloon, my p orbital represented either by two balloons or one long balloon squeezed together in the middle, and we bring them together so that this part and this part are pushed together, kind of like we did up here. Then we're creating a single covalent bond using an s orbital from one atom and a p orbital from another atom. So that's kind of how we're going to be modeling orbital overlaps in the valence bond theory. Now, let's take a look at this second paragraph here. Calculations show that when the distance between H atoms is 74 picometers, the potential energy reaches its minimum. That would mean it has a lot of stability, and therefore you can have two hydrogen atoms together to create that bond with a bond length of 74 picometers. It's very stable, and this is something that we can measure using X-ray diffraction. So if we come down here and take a look at this picture, and the best way to understand this picture is to begin at the right side and work our way to the left side. Let's check out the axes. Here we have our potential energy with positive going this way, negative potential energy going this way. In a sense, you could imagine, if we're talking about gravitational potential energy, as you lift something off the surface of the Earth, it has more and more potential energy. But if you go below sea level, like in Death Valley or the valley where the Dead Sea is below sea level, we could say that's a negative potential energy from the benchmark of sea level. And stability, of course, is going to be where something is going to be most stable. It's going to be as far down as it can possibly get, which around the surface of the Earth, the lowest elevation on the surface of the Earth would be way down here. So if we begin on the right side, here we have hydrogen atom number 1, hydrogen atom number 2, and of course if they're really, really far apart, those two hydrogen atoms are experiencing no attraction between each other. But as we begin to move them a little closer and closer together, and now we're looking at right here, in other words, as these two circular or spherical balloons begin to be pushed against each other, we find that the electrons of hydrogen number 2 are attracted to the nucleus of hydrogen atom number 1, and the electrons around hydrogen atom number 1 are attracted to the nucleus in hydrogen atom number 2, and we're beginning to create a single covalent bond of overlap. And we have a high region right here in the middle of electron density, where the reddish arrow represents the negative, the region within the molecule that has the greatest negative charge. Now, as we bring it a little bit closer together over here, we get even more attraction between the positive nucleus on the left and the electrons on the right, and the positive nucleus on the right and the electrons towards its left. And we continue on, and then at some point we get to a position where we have the most attraction between each nucleus, which is a proton, and the surrounding electrons. But now if we try to push them even closer together, we begin to see a tremendous repulsion. The one nucleus, the proton from the one hydrogen, is now so close it begins to experience a repulsion that is greater than the attraction between each proton and the surrounding nucleus. Also, all the electrons begin to repel each other. They're too close together. And even though there's an attraction between the electrons and the protons, the electrons are so close together, the density of electrons is so great that they begin to repel each other. And all of a sudden we get to a position right up here that is very unstable. So in this direction, we have an increase in stability. Going this way, we have an increase in stability. Certainly going this way, we have an increase in instability and repulsion, and we have this optimum position right here. And as we chart our distance between the atoms from 400 to 300 to 200 to 100, we find that the optimal distance between the two nuclei is 74 picometers. And that turns out to be the same place where we have our greatest amount of energy. This is the energy that is involved in creating the hydrogen molecule. And if you think about having a hydrogen atom and another hydrogen atom, you know that hydrogen atoms are very unstable because they have one electron, each of them, in their outer shell, and they'd like to have a pair of electrons. And so you gain stability when you get here. And so therefore, to create this hydrogen atom is going to be at 436 kilojoules per mole. And you're going to have the exothermic when you go towards the right, because you're releasing energy as you become more stable. But if you want to break it apart and become less stable, you're going to have to put energy into the system of 436 kilojoules per mole. So this is the most stable position. Now let's make sure we didn't leave any other things behind. So we already talked about the significant repulsive force when your two nuclei are too close together, and that actually is something you have to overcome when you want to fuse hydrogen atoms together, for example, to make helium, as opposed to a hydrogen molecule. And it's because you have to overcome the significant repulsive force. Let's see, we have this great agreement between theory and experiment. So we come up with these theories, we test them against experiments, and if our experiments support the theory, then we think we're on the right track. When our experiments do not support the theory, then we either abandon the theory or we modify the theory or tweak it in some respect. And then, of course, sometimes we do experiments, and the experiments produce information that is kind of remarkable and surprising, and we have to come up with a theory in order to explain that. So it can work in both ways. And as I was showing you in the picture down here with the two hydrogen atoms, we're talking about orbital overlaps, the merging together of the two balloons, where the surface of the balloon represents the region of space within which you'd find that hydrogen's electron 90% of the time, and we're merging these two balloons or these two orbitals together. And so the idea here is that bonds are formed by the overlap of atomic orbitals. And this is the basis for valence bond theory, because we're taking our valence electrons in their respective orbitals, and we are blending or merging or overlapping them together to create a bond. This, of course, when you bring two atoms together to create a bond between them, is going to distort the orbitals, just like when you have a balloon and you push in on the balloon with your finger, or you take two balloons like I've been talking about so far, and you push them together, their circular shapes become distorted. And the distortion results from electrons being situated so that they are attracted equally to the two positive charged nuclei. The electrons in hydrogen atom number 1 are attracted to the proton, the nucleus of hydrogen atom number 2, and vice versa. Now we're going to call this by a new name. This single covalent bond is now going to be called a sigma bond. And sigma, pictured here with this symbol right there, is the Greek letter S, and this is going to correspond to our s orbitals, which we say are spherical. Later on, we're going to be talking about a pi bond, and pi is the Greek letter P, and we're going to form those with our p orbitals. So that's how you can remember that. And so a sigma bond is a single covalent bond in which the electron density is greatest along the axis of the bond. So if we have this right here with our electrons are right on here, here's my axis. We've pushed the two balloons together along this axis to create this overlap between the two orbitals, orbital overlap. And now we have two electrons in that, those two orbitals that are now like one big orbital with the shape that looks kind of like this. And they must have opposite spin, of course, in order to coexist in the same orbital. Remember, the electrons are negatively charged. They should repel each other, and they do. However, if they have opposite spins create opposing magnetic fields, which is attractive, and that compensates for the repulsive force of the like charges. Because of orbital overlap, the bonding electrons have a higher probability. In other words, we're not saying this is a 100% prediction, but it has the highest probability of being found within the region of space. Now, what happens when with elements beyond hydrogen? As usual, we know hydrogen pretty well, and then it gets a little murky after that. So if we think about hydrogen fluoride, where fluorine is going to have its s orbital and its 3p orbitals, and so we can talk about fluorine looking something like this. And so you're going to have a single electron, and you're going to have 1, 2, 3 lone pairs. And one of these orbitals would theoretically used to be the s orbital, and the other three used to be the p orbital, until now when we connect it to create our molecule. The three lone pairs of electrons are said to be localized around the fluorine atom, as opposed to delocalized. This electron right here is going to be connected to the hydrogen. These electrons here are going to be localized. So this one can be delocalized, and then these are localized. I don't know if you like that language or not, but that's the language that's used. So a sigma bond, again a single covalent bond, results from the overlap of hydrogen 1s and the fluorine 2p orbital in the hydrogen fluoride molecule. And again, we can measure that distance. It turns out to be 92 picometers when the hydrogen and the fluorine reach that optimal position where this the hydrogen's proton right here is greatly attracted to the electrons, the valence electrons around the fluorine atom, and then the fluorine atom, I think I'll use the color green for the fluorine atom, it's greatly attracted to the hydrogen's electron, this is then going to create this hydrogen fluoride bond. And you can see that when we take a circular balloon and take our p orbital, which looks like a barbell shape, remember this whole thing is one p orbital with zero probability of the electrons being in the middle. And when we push this against that, the result is the picture here on the right. So you're used to drawing it like this. You probably would recognize a model like this, a space-filling model that doesn't show you the lone pairs. And then here's what our orbital notation is going to look like, or picture is going to look like. Now, what about in diatomic fluorine, F2, Brinkelhoff? So here we have my p orbital. Here we have my another p orbital. We're going to push them together till they reach the most stable position where each nucleus of each fluorine has the greatest attraction to the electrons of the other fluorine, not too close, not too far away. And you can see that this area, the right side of this single p orbital and the left side of these single p orbital of the other fluorine atom merge together to create this shape right there. And we obviously, when we push these two balloons together, pairs of balloons of necessity, and push them together, we can't fully make them merge like this, but you get the idea, I hope. Now, hybridization of atomic orbitals. A lot of this is going to sound very familiar. We're saying the same things that we learned about in Chapter 8, but we're using this different language now. And the book even reminds you that we're using the valence shell electron pair theory to first of all create our molecule. To draw it like this, you add up the total number of valence electrons, divide by 2 to get the pair, take your least electronegative element. Frequently, it's going to be carbon for inorganic chemistry. Almost all the time, carbon will be one of the central atoms, and then distribute the other atoms around the periphery, the outside, and then you see which electrons you might need to make sure every atom has an octet, except, of course, for hydrogen. And you might have too few, you might have too many, you might have an odd number. Those would all be exceptions to the octet rule, and might require you to invoke expanded valence or something like that. We also know that in three-dimensional space, these the orbitals where the hydrogens are connecting to the carbon are going to be tetrahedral in shape with a 109.5 degree bond angle, and you should memorize that number. So remember, this is what it looks like in 2 dimensions, and you have to think in 3 dimensions. Remember, the carbon, when you first learn to do electron dot notation, you put 2 electrons in the S subshell, and then 1 in the P sub X, 1 in the P sub Y, and then the P sub Z was empty. And we talk about the fact that why should 2 electrons be stuck in the same orbital here? Because they do repel each other, even though they have opposite spin, when you have an orbital right here that is empty. And so we hybridize that electron and we move it into its other orbital. So carbon's dot structure should be drawn like this. Again, that looks flat. It should be in 3 dimensions, meaning you're going to create 3 bonds, meaning you have 3 orbitals where those 4 orbitals, where those 4 individual electrons are, and then they can connect with the 4 orbitals of the 4 hydrogens. And our electron pair geometry and our molecular geometry are identical. They are both tetrahedrons with your carbon atom in the very center. And once again, remember that the shape of a p orbital looks like 2 spheres smashed together or overlapping each other, and that's not what's the case here. This is an individual p orbital, and the area in the blue and purple to distinguish the front lobe from the back lobe of the single p orbital represents the region of space within which you'd find this electron 90% of the time. And it's along the x-axis as well as the y-axis as well as the z-axis. So if you have 3 p orbitals, all of these would be on top of each other, and at the very center would be the nucleus of the atom that has these 3 p orbitals. So the theory of orbital hybridization is that these hybrid orbitals are created by mixing the s and the p's together when required. And a little bit later on, especially when we have expanded valence, we throw in some of the electrons or the d atomic orbitals in order to create these orbitals about the nucleus at the center in 3-dimensional space. And so when we look at the bullet points, number 1, the number of hybrid orbitals is always equal to the number of atomic orbitals. So you learned about atomic orbitals way back when we first started learning about quantum mechanics and talking about S and P and D and F orbitals. And we blend the orbitals together to make a hybrid orbital. Bullet point number 2, the hybrid orbital sets are always built by combining an S orbital with as many P orbitals and D orbitals as necessary. It might be no P or D orbitals are necessary. It might be 1 P orbital is necessary, maybe 2, maybe 3. An expanded valence, then we have to go maybe 1 from the D, maybe 2 from the D. By then we're up to an octahedral shape. That's usually about as far as it goes. And then third bullet point, the hybrid orbitals are always directed towards the terminal atoms. So the terminal atoms are the peripheral atoms, like the 4 hydrogens in methane or the 2 hydrogens in oxygen. Next, the hybrid orbitals required by an atom in a molecule or ion, that would be a polyatomic ion, are chosen to match the electron pair geometry of the atom. So we use the electron pair geometry because we need those lone pairs, because those lone pairs do occupy orbitals, just like the bonding pairs do. The bonding pairs are sigma bonds, single covalent bonds, and later on we're going to talk about double and triple bonds, which will be called pi bonds. So if we just have 2 orbitals, there's just 2 valence electrons in the molecule, so we're going to have 2 orbitals. And you'll notice we're really not distinguishing between an S and a P, so we're going to call each of those 2 orbitals an SP. And think of the letters SP as being one word. We have one SP orbital, and we have a second SP orbital. And we'll have some pictures of that in a minute. If we have 3 hybrid orbitals, those 3 hybrid orbitals will be repelling each other in 3-dimensional space and be 120 degrees apart, unlike if we only have 2 hybrid orbitals that will repel each other and be a full 180 degrees apart. But every one of those 3 orbitals will have the same name. One of the orbitals will be an sp2, the second one is an sp2, and the third one is an sp2. That's the entire name. So if we look at some of these pictures here, and here we have beryllium dichloride. And so this orbital here, and these are covalent bonds there, but each of these 2 orbitals, which is the result of merging the 2 orbitals together so that they overlap and reach the optimum distance in picometers, where you have the greatest stability, the greatest negative number of kilojoules per mole. These electrons are going to be distributed as far away from each other as they can. We have 2 regions of negativeness, to use my old language from before. It's going to be linear. So this would be beryllium dichloride. Beryllium, you recall, is in the second row. It's element number 4. So it already has 2 electrons in the inner shell, 2 electrons in the outer shell. Now, if we talk about boron trifluoride, boron is element number 5. So in the second row, it has 3 valence electrons, which will put as far away from each other as we can. And one, we would say 2 of them are an S, and 1 of them is a P, but we don't distinguish between the S and the P. We're going to call them all by the same name. They're all going to be called, this is going to be an sp2 orbital, there's an sp2 orbital, there's an sp2 orbital. We bring them together to their optimum position right here, where we have the greatest stability, and that's going to be trigonal planar. And then when we look at 4 electron pairs, And remember, these electron pairs might be bonding pairs. They might be lone pairs, like in water and ammonia in this illustration. But this is methane. So we don't distinguish between the S and the PX and the PY and the PZ. Doesn't matter which one you call the X, the Y, and the Z. We're not going to call it that anymore. We're going to call them all the same. They've been hybridized. So they're all the same. They all look the same, so to speak. They're all in sp3. So since you have an SPPP or sp3, you have a total of 4 letters, which means you have 4 orbitals. Up here with boron trifluoride, you have an S and a P and another P. You've got 3 letters, so you're going to have 3 hybrid orbitals. And then down here, you're going to have 5 hybrid orbitals. You're going to have the 1 from the S, you're going to have the 3 from the P, PX, PY, PZ, and then you're going to borrow 1 from the D because you have expanded valence. But you're not going to distinguish. You're not going to say that the S somehow looks different than the P or that P or that P or the D. So we call them all the same thing. You have 5 sp3d. So there's an sp3d, 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 an sp3d in there, and an sp3d there. And when they reach their most stable configuration, it might look like that, with the overlapping of those orbitals, and it's trigonal planar. You've got your phosphorus, in this case, in the very center, and then around the equator, you've got this atom and this atom and this atom around the equator, and then at the North Pole and the South Pole, you've got 2 more of these fluorines. And then finally, like I've been saying all along, when we have this type of expanded valence where we're borrowing 2 electrons from the D subshell, you have 1, 3, and 2, which equals 6 orbitals, and they're all going to be identical. We're going to call all of them sp3d2. sp3d2. 5 syllables to talk about every one of these 6 orbitals that are going to overlap into the most stable configuration. This would be octahedral. And now let's take a look down here. What about using the valence bond theory for methane? Talking about methane again. And so we might have, when we think about what we start with, this is position number, or drawing number 1 at the very top. And I'm calling this the initial configuration as you originally learned it. The lowest energy, we're not counting the 1s subshell, but in terms of valence electrons, you've got the 2s subshell. And then once the 2s is filled, we move up to the 2p, and you have the x and the y and the z, and you put 1 in the 2px, 1 in the 2py, and now you've run out of electrons for your carbon. Remember, carbon is going to have 4 valence electrons. And so there's your first one, and there's your second one, and now you filled up the 2s subshell, and so you put the third one there and the fourth one there. Remember, monopoly, you have to put 1 electron in each of the 3p orbitals before you can pair them up. And so we might say, well, therefore, again, carbon should look like that. There's my 2 in the S, and there's my PX, and there's my 1 in the PY. Well, we immediately had learned that, no, we're going to stick that electron up there. And so when we move from this picture, and now we're down to this picture here, once we've hybridized these orbitals so that they're all the same, it looks like this. And so what are we going to call each of these right here, each of these 4 orbitals? We are going to call each of them an sp3 orbital. So sp3 orbitals means you have 4 of them. If you have 4 orbitals, then they're all sp3. And that's applying the valence bond theory to methane. Now, because there are no lone pairs, methane is a nonpolar molecule. And in this edition of your book, the previous edition of this book, by the way, did not have as easy a way of printing things in color. And the technology advances from edition to edition. So this is very helpful. You can see that we've got blue, which is going to represent something, compared to red, which is going to represent something. And you can choose whatever color coding you want. But we use the red to represent high electron density, and we use the blue to represent low electron density. And if you consider the fact that hydrogen only has one electron, I'm going to come over to this drawing now. If that electron for hydrogen is there, and I'm going to switch to red. If that electron is there, and there, and there, and there, for the 4 hydrogens being shared with the carbon, that means that the surrounding area doesn't have any electrons, and therefore, by comparison, is going to be positive. And in 3 dimensions, your picture, back to the right now, the blue areas are representing the positive regions, and the red areas with high electron density are representing the negative regions of the entire methane molecule. And there's your bond angles. There is your shape. No matter which model you use, the electron or geometry you use, molecular geometry, electron pair geometry, it is tetrahedral. Now when we move to ammonia, NH3, we now have a lone pair, and that lone pair is going to be right there. You see it there, you see it there, you see it there, and in color coding it creates the red region, and then this area and this area and this area by comparison are going to be positive because they are bereft. That means they don't have any electrons. That's going to be the positive region, very positive, not quite so positive, and eventually it merges into being negative as we get towards the polar end. So now we have a polar molecule, not to be confused with a polar bond. And using our Vesper model, we anticipate, or we would know, we have tetrahedral electron pair geometry, because again, when we think about regions of negativeness, there's a region of negativeness, and there, we got 4 regions of negativeness that are going to push our toothpicks. Let's do it over here. We have a region of negativeness there, and there, which in 3-dimensional space pushes each particle or each pair of electrons as far away from each other as you can get. So it is going to be tetrahedral in terms of electron pair geometry. In terms of molecular geometry, where we only concern ourselves with the atoms in the molecule, we would say that it is trigonal planar. We learned about that in the last chapter. And because one of the things that we learned is that when you have a lone pair of electrons, like here, and they're not being stretched between 2 atoms, that region of space where those 2 electrons are, they sort of bulge outward because it's not stretched skinny. Instead, it's more rounded because there's not 2 positive areas that are stretching the electron region into a narrow area, which we would call a bond. Therefore, this pushes on the shared pairs and pushes them a little closer together. And so we move from 109.5 to a little bit less, which is 107.5. Now we can do the same thing with water. By the way, notice that around ammonia, every one of those 3 orbitals, merged orbitals, blended orbitals, overlapped orbitals, all 4 of them are sp3s, even though one involves a lone pair and 3 of them involve a shared pair. You have 1 lone pair, 3 shared pair, you have four orbitals that overlap. So it's sp3 hybridization. We include the non-bonding pairs, the lone pairs. When we come to water, now we have two lone pairs, which are going to bulge outward because they're not stretched thin between two nuclei, which are going to push on these shared pairs, and now my bond angle gets even smaller from 107 whatever down to 104.5. We have a bent or angular molecule, but we still have 1, 2, 3, 4 regions of negativeness. We have 4 orbitals that are overlapping. And so once again, we have sp3 hybrid orbitals, where we ignore the difference between a lone pair and a shared pair involved. And we have our nice color coding again with our strong negative region and our nice positive regions right here, where the hydrogen atoms only have their nucleus exposed. And so we have a very polar molecule. Now we can look at ethane and begin to get a little bit more complicated, where now we're going to have 2 central atoms, each having 3 carbons. And we are going to merge or blend or overlap 4 regions of negativeness. There, and there. And this one is there, and there, and those two become 1. And so each carbon atom has 4 regions of negativeness. So we have sp3 hybridization all the way around, and tetrahedral for around both carbons. And this is what it would look like, where you would have most of your positiveness of your this atom would be around here. And your electron density, of course, is greatest in here. But because there's no one side, the top side is not more positive or negative than the bottom side, or the right side is not more positive or negative than the left side, or the front of the molecule is not more positive or negative than the back of the molecule. This is going to be a non-polar molecule. And you're going to have 109.5 degree bond angles. So anytime you have sp3, we expect 109.5. Anytime you have sp2, we expect 107.5. And anytime you have sp1, in other words, just sp, we talk about 104.5. Now, these numbers are different in different textbooks. Sometimes you just see whole numbers. Sometimes there's 9s there. So there's a little variation from textbook to textbook. All right, what about in methanol? Again, we have 2 central atoms. We've got an oxygen atom there and a carbon atom there. We should know from experience that we have 2 lone pairs right there. You can see them right there. And therefore, we're going to have a bent molecule here, bent. And just like water, imagine, for example, that instead of this, we had another hydrogen. This is 104.5 bond angle there. But then coming down to the carbon, which is right there, we've got 1, 2, 3, 4 regions of negativeness in 3-dimensional space. So here we're going to have sp3 hybridization all around the carbon. And because we include the lone pairs, we have sp3 hybridization all around the oxygen atom as well. But our bond angles are different. The bond angles down here will be 109.5. Tetrahedral around both as well. All right, what about trigonal planar electron pair geometries? And there are 4 very common examples for trigonal planar. And sometimes they're worth memorizing because they're so common, especially the nitrates and the carbonates. And we're going to be creating 3 hybrid orbitals. So let's come up and take a look at the picture. And the way we would initially draw this, if you think about it, way back in first year chemistry or a few chapters ago, before we did a deep dive on bonding, we would say that as far as boron is concerned, since boron is element number 5 and it's the third element in the row, you're going to have 2 electrons here. I'm sorry, not 2 electrons. You're going to, yes, 2 electrons for the 2s, and then 1 electron for the 2p sub x. But that leaves us 2 open orbitals, so if we hybridize and stick an electron up here and make our electrons as far away from each other as we can get them, we go from this drawing here, where we filled the S subshell before we filled the P, off-bow principle, remember. We come down here and we distribute the electrons around all available orbitals. Sort of Hund's rule, put 1 electron in every available orbital before you go back and double up. And that means we only have 3 orbitals involved. And you might say, what are we going to call them? Well, we're going to call them sp2. This is an sp2 orbital. This is an sp2 orbital. This is an sp2 orbital. Each of the 3 sp2 orbitals are a hybrid of an s and a p orbital together. And we distribute them. And when we distribute them, we get a 120-degree bond angle. We have sp2 hybrid orbital notation. It's trigonal planar because it's flat. When you spread them out as far away from each other as you can, it ends up being a trigonal planar flat molecule. And this is our electron pair geometry, where we don't have any lone pairs around boron. And what about a linear structure? In this case, we talk about beryllium. Beryllium element number 4. It is the second element in its row. The way we used to draw it was we put 2 electrons in the S, the 2s that is, and we filled it up. No go in the 2p. However, when we hybridize those orbitals right here, one was the instead of calling one an S and the other an S, we call them both an SP and an SP. SP. Or that looks more like S pi. There's SP. But think of SP again as one single word. And so what we have here is an SP orbital, and we are going to overlap. The SP orbitals are overlapped, and when we put them together, we create this structure over here. And so we have 2 regions of negativeness, one there and one there. We spread them as far apart from each other as we can get, which is 180 degrees. And you can see that this is a linear structure, forms a straight line. And then we can move in the direction of expanded valence, and I'm going to stop right here and we will pick up in the next screencast.